Good afternoon, this is Schweitzer. We're going to look at our second of our SMART videos on properties of substances, and we're going to walk through not only dissolving properties, but also a couple of practice questions on both dissolving and melting point. So we just cut the last one off because it just didn't want to get too long. So here we go. First question is, why do things dissolve? And this is a really important question that we want to make sure that we understand. Whenever something dissolves, of course we have the solvent. Alright, and let's put this over to a black pen just because. Alright, and then we have the solute. If you were to drop solute into solvent, let's just say we have a beaker here, and of course if you drop a rock into water, it just falls down to the bottom. And at some point, maybe that item isn't a rock or maybe something else, and it just simply floats. Okay, so there might be, we could go into the concept of buoyancy here, because but that's not really our intent here. Small particles like that, yeah, granted there is some buoyancy there, but in this case we're really looking at a balance between the attraction between the solvent and the solute, the thing you're dropping in. So the thing you're dropping in is the solute. Anytime we want to reference why something dissolves, you want to reference this particular type of attraction. Of course, there is only one type of attraction we have, which is Coulombic. And that's just, the Coulombic would be various versions of why things dissolve. Various versions of intermolecular forces. The most common one here really would be ion dipole. That would be where you have water or something else, for that matter, where it's got a dipole on it and it attracts to an ion, which is positively charged. So we have that attraction there. So anytime, though, you're looking for comparing solubility, we always want to reference the attraction between the solute and the solvent. Okay, we'll be looking more at ion dipole as we go through this particular property here, or this particular set of notes. Alright, so any of these could be utilized, but really for our purposes here, this is the one that we're gonna, mainly focus on. It's an opportunity to use that one. How do we model a dissolving substance with a written formula when dissolving? Okay, so write a dissolving formula for potassium nitrate. Okay, so potassium nitrate is KNO3. And of course, what's it look like? This is one model that we're using to describe what's happening, a phenomenon in a beaker. So the two ways we'd show it would be one with a particular particulate diagram, which of course will be on like the next slide. But what happens to an ionic compound is it dissociates. That's real important, that the ionic compound dissociates as it dissolves. So it breaks apart as it dissolves, but we're going to break into potassium ions floating around and nitrate ions. So this thing here, this thing is molecular. So you could draw a Lewis structure of this thing, correct? With all the electrons on here. Alright, so this thing is a whole very tightly bound molecule. So we wouldn't want to separate that particular thing. We keep it together. So it's separating. So that's what it looks like in a beaker. How would we draw that on paper? So they show it together here, and they just say K plus NO3 minus. Now, one thing about this is that the reason why this thing is dissolving is because of that charge there. So that's a really big thing that you want to make sure you include right here. Right? If I take that charge away, this thing drops out like a rock. I mean, we'll see chemical reactions that will strip away that charge or neutralize to zero, and it just falls out like a rock immediately. So the reason why it's in dissolving is because of that charge. They really is a big focus point to make sure you don't forget those charges. Post them here. You could add an aqueous here if you wanted to.
for most people in this business, they would realize that because it's separated means it's dissolved, but that would be maybe a little extra information here. Again, you want to go a step farther, you could put a solid here. All these things would be likely something that on an AP style problem would not be part of the
rubric to answer the question. The charges, however, they would be. Alright, so practice writing out dissolving equations. Take a moment, pause for a moment here, and give these a try. Okay. So the first one we're looking at here is magnesium chloride. So one of the things we kind of got to be aware of is these ratios that occur here. So a 1 to 2 ratio is something that in a pictorial diagram also would be very careful. You'd have 1 cation for every 2 anions because the cation is positive too. So be aware of that. The biggest thing here that we're trying to, the questions that I gave you, be one, practicing your translating of your names, yes, but are you able to accurately depict these ratios? And are you understanding that which things are molecules and therefore wouldn't break apart? Meaning that this is a molecule. So this is going to be AlPO3. Now this is a -3 plus 3, so it's 1-to-1 ratio. It's just going to be Al plus 3 plus PO3 minus 3. 1-to-1 ratio. Ammonium sulfate would be NH4 parentheses 2SO4. You hopefully are getting to the point where you can just start writing these out. This is going to form 2 NH4 pluses plus an SO4 minus 2. So that produced 3 particles. This produced 2 particles. This produced 3 particles. Those number of particles sometimes can have a difference in some properties of chemistry. Alright, so Fe, you got a little thing here. Good practice. NO3 and 2. There we go. We'll produce Fe plus 2. And then the plus NO3 minus 1. All good stuff that you'd want to be able to do. Alright, now, using a beaker to model solubility. These are really common questions they'll have actually on AP exams, and you just have to add in things. They'll have add water molecules or add aluminums. They'll tell you. So first let's write this out here so we know what's going on. We have aluminum chloride goes to aluminum plus 3 Cl minus. So there's 2 ways they might depict you to do this. One is going to be with just without the solvent. They just want you to show it this way. So it'd be Al plus 3 Cl minus, Cl minus, Cl minus. A few things they're going to kind of want you to be aware of is that the size of the atoms. They might ask about that. So they might have something like this. I'll exaggerate it here, and you pick out the right one. Now I have these all together here, but really they're all floating around. And this one's a little smaller. And why is that? This guy here is isoelectric with neon, and these guys here are isoelectric with argon. So they would be a little bit bigger, having extra energy level. So size of atoms is sometimes in question. The quantity of atoms always in question. So again, I should have probably separated these out a little more and float around, but they're definitely separated floating around. That's your spatial location, ratios, things of chlorides, aluminum important. The other option they do is where you literally show what's called solvation. Sounds like a religious term, but solvation would be another term for dissolving. And they want to show you how the actual water molecules are grabbing onto these ions, showing the ion dipole attraction. So this is the positive version, since this guy has got the negative on this side and the positive on this side with the hydrogens. I just want to show this like this, and I would just have to do that. They're never really going to ask you to label anything. They're just going to want you to show it like so. And be very careful that you indicate that this is the positive, this is the negative, that you're not giving them any reason to not to give that point. Reading directions and that thing is a little bit key. They may ask you to add 1, they may ask you to add 2, they may ask you to add 10. I mean, it's just part of it. So a property of a dissolved solution is called an electrolyte or a non-electrolyte. There might be another one called a strong or a weak electrolyte. And it really has to do with the amount of ions dissolved. So the ions, only ions dissolved. Now, I mentioned to you before, like how one item will break into like 3 things, or one item will break into 2 things. Well, the more ions you break into, the more you can conduct. So that would be one example of where how you're breaking apart really does kind of make a difference. So either way, here we have an example where there's ethanol and there's no charges present, so it's non-conductor. Potassium chloride is going to have a +1, -1, therefore be a high conductor. And of course, the more ions you have present, the more your light bulb lights up. So you could increase your concentration of these things, or you could use a salt that breaks into, let's say, aluminum chloride. That's going to break into 1, 2, 3, 4 different ions. So for one of these produces 2 ions, one of these produces 4 ions, and that's important to kind of realize. Here's acetic acid. Okay, so we haven't learned about this too much yet, but acetic acid is HC2H3O2. That's not an ion, but it undergoes hydrolysis when it produces its acid, which would be H+ ions and C2H3O2 negative. So it's dimly lit, so that means it is doing this, just not a lot, just a little bit. Okay, so there's some of that present, but mostly it's this. Okay, a little harbinger of things to come there. How do you separate a solute from a solvent? Okay, that's really important here. So if I have a particular thing, if it's truly dissolved, it's just going to stay dissolved. It's forever. You know, our oceans don't have piles of salt on the bottom of the floors. But that being said, if it's, you know, there are other things called a suspension. I think that's spelled right. Suspension. You have a colloid. These are things that, based on the size of the particle and the mass particle, the weak attractions are holding them in there, but really over time, gravity is going to pull it out, and it'll eventually separate into 2 different situations here. But if it's truly dissolved, you can even filter it. Even a filter is something that will not be able to stop something truly dissolved, and that's really important. Okay, a filter would definitely have no problem getting rid of suspension. A suspension would be like taking a bucket of dirt, you know, dirty water, looks brown, and then over even 5 minutes of low turbidity or low messing with it, it all just sort of falls to the bottom and this turns clear. A filter would knock this stuff out immediately. A colloid, very similar. It would gum up this filter quite a bit. So, all right, a couple problems here. Again, just looking to see what was this model looking like. There's a couple ways you can know. Is it, you know, what is this thing? First of all, I mean, this thing's ionic, because you know, or it could be metallic. But if it's got a cation, I'm thinking it's probably going to be ionic. So, is this an example of a molecule? No. Is this an AI? No. Because of the ratios here. So it should be NaI. Alright. Next one. Which of the following is true relative to a model provided involving elements of sodium and iodide? There we go. I think we just do this one. Looks like I have... Okay, another one here. Another example. 2 different questions. Would this substance break apart as it dissolves? Yes, because it's ionic. Melting the substance would break an ionic bond? Yes, it would. Alright. Alright, so this is an interesting question involving what's called a solubility curve. Great chart, great to read. So we're dissolving things, and in this case we have a 220-gram sample of sugars added to 20 degrees. The solution is stirred. The mass filter papers, they're going to filter it then. So something that's truly dissolved will not break out will not be able to separate it out, which of the following is true. So at 20 degrees, you should note, and you should be trying this on your own. If in class we will. Okay, you can take 200. So technically, this thing is only going to be able to hold 200. So 20 would not be able to be dissolved, and therefore, I believe the answer, the paper should weigh 22 grams since the solution was saturated. So 20 is from the mass of the solid, and 2 is from the actual filter paper. I believe that would be what it is. And there we go, another one. Okay, solution shows correct sizes and ratios. Alright, the solution shows correct size. So magnesium chloride, we have 1 magnesium, 2 chlorides, yes. So this is yes. Are the sizes yes? Chlorine, this chlorine should be bigger. I think this one's out because of sizes. Placement of atoms, yes, they are correct. Placement, just that's the problem. Solution is attracted to by a dipole attraction. This is a no, it's the ion dipole. So really it's neither. Okay. And thank you very much.